So we've had a ton of snow days and we need to get caught up. So I'm going to go through the acids and bases PowerPoint with you, specifically making sure that I do some example problems. You'll find that this is really similar to what we were doing before. We're still using ice problems, and really all we're doing is adding on a calculation of pH or POH to the end of the problem. I'm going to start at the beginning. With acids and bases at the very beginning and just redo the whole lecture. This is a one take, so there's going to be mistakes. There's probably going to be announcements coming on. Just go with the flow. Okay, so acids and bases. We talked about these definitions earlier, so this is just a review. Remember, our Arrhenius definition is our pretty limiting definition of both the acid and particularly the base, because in order to be a base, you have to have hydroxide, and only our strong bases have hydroxide. The better definition that we use is the Bronsted-Lowry definition, where we still are talking about acid being a hydrogen donor or producing hydrogen. Remember that the hydrogen ion is also referred to as a proton. And so we have our acid as a proton donor, and we have a base as a proton acceptor, and this really opens up our definition for bases. We're going to see now how ammonia, which we know to be a base, produces hydroxide. We had a few more definitions that we had to go over. I'll put these up real quick here. Our conjugate acid, our conjugate base, and then remember that there's the relationship between the conjugate and what it came from, which is known as the conjugate acid-base pair. Our conjugate acid is the base molecule plus a hydrogen. Conjugate base is the acid molecule when you get rid of one hydrogen. And these two things are related to each other by one hydrogen. There's just the difference of one hydrogen. So for example, whoops, that's not a good color. NH3 and NH4 plus 1. They are conjugate acid base pair. They differ by one hydrogen only. On our acid dissociation, you're going to notice I changed a little bit on this slide. Up here at the top, the part that I changed is I decided I liked it better with the H3O, the hydronium, in there for you, because then I think it makes it really easy to see the acid, the base, the conjugate acid, the conjugate base. And remember that our acid and base will always be on one side of the arrow, and our conjugate acid and our conjugate base will be on the other side. And so what we're looking is to see, how did things change? How did H2O change? Well, H2O became H3O plus 1. It is plus a hydrogen ion, and so this must be our base. Well, if that's the base, this automatically has to be the acid. Now over here, the base plus a hydrogen, that's our conjugate acid. And over here, our acid minus our hydrogen, there we have a conjugate base. And if you notice in the way where I put the arrows in, you also can see where we have our conjugate acid-base pairs. Notice between the H2O and H3O plus 1, there's a difference of one hydrogen. And between the HA and the A minus as well, there is a difference of just one hydrogen. So there are two conjugate acid-base pairs present. Now the part that we really care about down here is that once again, at the bottom, we're going to be able to do our equilibrium expressions again. And remember, we're just changing this one up to a Ka. We do it the same as we did it before, products over reactants, but we're using Ka this time for the acid dissociation constant. And this, get everything up here. Difference between our strong acids and our weak acids. First off, you have got to memorize those strong acids already. With our strong acid, our equilibrium lies far to the right. And remember, we're going to see a difference in the arrows. Our strong acid, the arrow's only ever going to go one direction. It lies so far to the right that we'd actually never make it back to the left. In our weak acid, there is an equilibrium, and so we are going to have arrows going both directions. So sometimes it's just as easy as looking at what kind of arrows there to know whether it's strong or weak. With the strong acid, all of our strong acid has dissociated, but in the weak acid, we got a lot of that HA present, that we still have a lot of weak acid there. In terms of the types of conjugate bases it produces, the strong acid, it yields a really weak conjugate base. That conjugate base is so weak that it can't attract the hydrogen to force it back to the left. So that's why that arrow only goes one direction. It only goes to the right because our conjugate base is so weak it can't attract the hydrogen. It can't make it back the other direction. Whereas with our conjugate base of our weak acid, that's a pretty good conjugate base. It has the ability to attract that hydrogen ion. It's really good at doing that and pushes it back to the left. So even though we do have an equilibrium here, we'll see that it lies far to the left. We do get some dissociation. We dissociated these acids, and really the important thing I want you to remember on this slide is look at the arrows. The arrows are important because the arrows are going to tell you whether we're dealing with a strong acid or a weak acid. Hydrochloric is strong, so the equilibrium lies far to the right. That means chloride here, which would be our conjugate base, horrible base. It can't attract that hydrogen ion back and go the other direction. Whereas down here, in the second one with our ammonium, our ammonia, which is our conjugate base, is really good at getting that hydrogen ion, so it can force its way back to the left. You know, here, I only threw this one in because we've been talking about complex ions, and there we've got a complex ion. Now, anytime you have more than one hydrogen ion, it can be referred to as polyprotic, diprotic, triprotic. It just is referring to how many hydrogens are present. An interesting case here is with sulfuric acid. Notice the arrow on sulfuric acid is one way in the first dissociation. But when we go to the second dissociation, now we're heading back the other direction because that's a weak acid, the second dissociation. So in terms of talking about conjugate bases here, if we wanted to mark which one of these is a better conjugate base, is this a good conjugate base or is that the good conjugate base? In this case, we'll put stars here. That's the better conjugate base because notice the arrow, it's going both directions. Okay, so now we're kind of heading into where some of the stuff might be new. I don't think sixth period we got this far. Ka is inversely proportional to base strength. So as the Ka goes down, so, and we're talking numerically, the Ka is getting smaller and smaller and smaller, then the base strength gets stronger and stronger and stronger. And if you think about it, it goes all back to the equilibrium expression. If we're thinking about Ka, and we'll just do real generic H plus A minus over HA. In our weak acids, the equilibrium lies far to the left. So what's going to happen is this number right here is going to be a lot bigger than these numbers. Well, when your denominator is bigger, that means your Ka gets smaller. So it all comes back to looking at that equilibrium expression. You can remind yourself by looking at it how the Ka gets smaller. Well, as the Ka gets smaller, the base strength gets stronger. And actually, let's even throw in conjugate. It's a little sloppy. Conjugate base strength gets stronger. And I think there's some animation in here. And well, yeah, there we go. The weaker the acid, the smaller the Ka, the stronger the conjugate base. And so what I have here for you is we have a couple of conjugate bases, and what we want to do is we want to organize these in increasing base strength. Well, you're not going to be able to go to any chart and look up the bases. What you need to do is take these and look up their acids and figure out which one is the weakest acid or which one's the strongest acid to come up with the proper sequence. And to help you with this, you make sure you put a Post-it in on page 658 of your textbook, page 658 of your textbook. You could also, if you wanted to, put a Post-it in on page A22 and A23. A22 and A23. There are listings, Ka values for acids, weak acids, and Kb values for weak bases. So, let's go ahead and go back and look at those and start working this problem out. So we had H2O, F minus, Cl minus, NO2 minus, and Cn minus. And these are all the conjugate bases. Now below, what I would do is, with everything with the exception of water, is take it back to its acid. And all you have to do to take it back to its acid is we're going to add a hydrogen ion to it. And that'll tell us about the acid that it came from. So here, first one, F minus becomes hydrofluoric. Chloride becomes hydrochloric. Nitrite becomes nitrous. And cyanide becomes hydrocyanic acid. Now these four acids that we have up there, they are all represented on page 658 with a Ka value. And remember, as our Ka goes down, our base goes up. And for some of you, we had, I think, definitely fourth period, maybe sixth period, we had made a little chart of information. We had talked about, we were going to put water in the middle, and because it's an in-between base. It's in between the conjugate bases. We'll put conjugate base of a strong acid. It is a better base. Water is a better base than any conjugate bases of a strong acid, but water is not as good a base as the conjugate base of a weak acid. So that'll help us organize a little bit. One of these acids, and hopefully you know which one, is a strong acid, which is our hydrochloric. The conjugate base of a strong acid is weaker than water. So we'll start this off with chloride. Then comes our water. And then these three remaining acids that we have up here, we need to figure out, these are all weak acids, but now we want to organize them the strongest of the weak to the weakest of the weak. Because remember, as the K goes down, that means you have a weaker and weaker acid and a stronger and stronger base. So when you go to page 658 and look at that, you'll see you have hydrofluoric, which has a Ka of 7.2 times 10 to the negative fourth. We have nitrous acid, 4.0 times 10 to the negative fourth. And then down there at the bottom, we have hydrocyanic acid at 6.2 times 10 to the negative 10th. All you have to do is, these are already in order from the strongest acid to the weakest acid. So strongest to weakest acid is weakest to strongest base as well. So we'll just put them up there in order. We'll have our fluoride, our nitrite, and then our cyanide. Largest Ka value, so weakest conjugate base. Little bit smaller value, it becomes a stronger conjugate base, and this one was really small at something to the negative 10th, so it's the best conjugate base that we have. Okay, amphoteric. These are substances that can behave as either an acid or a base. And our best one to talk about is water, and its auto-ionization. We have water as a liquid, and when it breaks apart into hydrogen ions and hydroxide ions. And in this chapter, you're probably going to find it more useful to think of water like that. Instead of H2O, you'll see me more commonly write it as HOH. And see, it produces both hydrogen ions and hydroxide ions. Notice we also have an arrow going both directions, so that means we can write an equilibrium expression for this. Notice this time it's a KW instead of a K, a KA, KC, KP, all the different Ks. And also, remember, we always leave out our solids and our liquids, so that's why you don't see water appearing in this particular equilibrium expression. We only have the hydrogen ions and the hydroxide ions. This is a super useful equation, that's why it's in green. And you actually, the KWs of water, there is a chart of them based on temperature. And you'll see that 99% of the problems that we work through, we're always at 25 degrees Celsius. So this means that no matter what problem you're working with, if you happen to know, for example, how much hydrogen you have, you can solve for the hydroxide because it's at 25 degrees Celsius. You automatically know what the KW for that would have to be. If you happen to know the hydroxide, you could solve for the hydrogen. And the reason that you can do this is no matter what solution that you're looking at, you always have some of both. You always have some hydrogen and you always have some hydroxide. What happens is some of them you have more hydrogen than hydroxide. Some of them you have more hydroxide than hydrogen. And sometimes they're equal to each other. But in every single case here, you always have some of both. So even if you're working a weak acid problem and you're solving for the pH, there is still hydroxide ions present, and there still are, you can still calculate the pOH for it. So I think that's one of your first questions in your Zoom doll. It asks you, you have a strong base. Does that mean there isn't any hydrogen ion? No, doesn't mean that. There's always some. It may be a teeny tiny amount, but there's always some present. Okay, so pH scale. This is in your textbook. I didn't put a copy of it here because it doesn't look very nice on this PowerPoint. But everybody always asks, what does the P stand for in pH, POH, whatever? What the P means, P always means take the negative log of whatever you're representing. In this case, for the pH, we take the negative log of H. In POH, we take the negative log of OH. We can take a pK, and a lot of times it's a pKa or a pKb, negative log of K. As well, this is my favorite equation, because a lot of questions will ask you to solve not only for the pH, but the POH. And this is a handy dandy little problem formula to use to make it really easy to go from one to the other. Now, something that I hadn't put in this PowerPoint before, but I want to go ahead and talk about is, can we reverse this process? What do you do if you have a pH and you want to come up with the H? So we have the pH, and this time we want to know what is the hydrogen ion concentration. To do that, you take the inverse log of the negative pH. Inverse log on your calculator, you're just going to do the second log on your calculator and then put a negative in whatever the pH is. It works the same way if you wanted to find the hydroxide from the POH. It would be the inverse log of the negative POH. So you can practice a few of those. I'm not going to do any of these with you right now, but you could try these in your textbook. They're pretty easy problems, 14.3 through 14.6. And let's move on. Let's go ahead and talk about pH of strong acid solutions, and then we'll actually do a little work with the weak acids, and then we're going to just take exactly what we've learned with those things and move it in to bases. There's only one minor adjustment we'll have to make. Okay, first thing you always want to deal with is what are the major species that are present. And pretty easy, all you gotta do is dissociate your acid and always remember that water is present. And the reason that water is so important, that we've got to continue to include it, is remember that water auto-ionizes. It's always going to produce some hydrogen and it's going to produce some hydroxide. So we have to consider it because occasionally water is a better acid or a better base than what we're looking at, the acid or the base that we're actually concerned with. So you always, for example, if we were working with 1 molar hydrochloric, there's no HCl altogether here. That molecule doesn't exist anymore because this is a strong acid. It really dissociates into hydrogen ions, chloride ions, and there's also water there. But you need to remember this water also breaks itself down into hydrogen and hydroxide. So we always have to consider all the components of water as well as we're doing our calculations. Okay, so let's do a few problems here. We're gonna let's calculate the pH of 0.1 molar nitric and the pH of 1.0 times 10 to the negative 10th molar hydrochloric. Now, both of these, you know, nitric and hydrochloric are classified as strong acids. So if you were in class right now, I'd ask you what kind of arrow. They should have arrows going one way. So let's start with the pH of 0.1 molar nitric. Okay. Now with our nitric acid, let's dissociate it. Now remember, one way because it's a strong acid. And that's going to give us our hydrogen ions and our nitrate. Remember, nitrate is a poor conjugate base. It's not even as good as water. Mentioning water, water is still here. And it auto-ionizes into hydrogen and hydroxide. And what we need to decide is which one is the better producer of hydrogen ions. Are we getting more hydrogen ions from our nitric acid, or are we getting more hydrogen ions from our water? And I kind of cramped this a little bit, so let me leave a little space here. Okay, so we know that this is 0.1 molar, and based on mole ratios that exist, we have a 1:1:1 ratio across here. So that means if our nitric acid is 0.1 molar, our hydrogen is 0.1 molar, and not that we really care, but our nitrate to be 0.1 molar as well. Well, we got water here, and water does auto-ionize. And remember, we had a kW for this. It was 1.0 times 10 to the negative 14th. Well, using that, water, as we know, is neutral. And if we wanted to, we could actually solve for, and you'll probably end up memorizing, the concentrations of hydrogen and hydroxide. Because this is neutral, neutral means our hydrogen has to equal our hydroxide. And so they're going to be the same. So we can set them both equal to X. Well, kW equals X squared. And so if we wanted to go ahead and solve and find out what the concentration of each would be, we would just take the square root of our kW. Take the square root of 1.0 times 10 to the negative 14th, and you get 1 times 10 to the negative 7th molar. So now we know concentration of our hydrogen ions and our hydroxide ions for our water. And remember, most of these problems are going to be at 25 degrees Celsius. So I would memorize the fact that the concentration of hydrogen and hydroxide are 1.0 times 10 to the negative 7th molar, because once again, 99% of the time, that's the way it's going to be anyway. So who's contributing here to our hydrogen ion concentration? Is it getting most from here, or are we getting most of them from our water? It's really easy. It's whichever one's the bigger number is the bigger contributor. So in this case, if we wanted to calculate the pH of this particular solution, all we would need to do is look at our strong acid, because it's giving us the majority of our hydrogen ions. So pH equals the negative log of our hydrogen ions. pH equals the negative log, and here, let me show you a trick. Let's put this in scientific notation. As long as your coefficient is 1, it only works when the coefficient is 1. When the coefficient is 1, then, oh, whoops, all you have to do to come up with your pH is take the opposite of the exponent. When the coefficient is 1, all you have to do is take the opposite of the exponent. So negative 1 becomes 1. So the pH of this is 1.00, which is pretty common for strong acids. They tend to be in 0 pH, which yes, you could have a 0 pH, or they have a pH of 1. That's pretty common. Okay, so that's our first problem. The other one we had was to find the pH of 1.0 times 10 to the negative 10th molar hydrochloric. Let me check and see if I have an extra slide here if I need to put one in. Oh, yep, let's go back. Okay. There we go. Okay. So now we're doing the pH of 1.0 times 10 to the negative 10th molar hydrochloric. And once again, we will first dissociate our strong acid with an arrow going one direction. We can go ahead and think about our concentration. This is 1 times 10 to the negative 10th molar. There is a 1-to-1 ratio that exists all the way across here, so everything is 1 times 10 to the negative 10th molar. Now, don't forget we also have water present. It auto-ionizes into hydrogen and hydroxide, and of course these are all at 25 degrees Celsius. At 25 degrees Celsius, we know both of these are 1 times 10 to the negative 7th molar. Now we want to look at all of our species that are present, and we've got two places where we are producing hydrogen ions here, both from the strong acid and from our water. And once again, we're looking for which is producing more, which one's got the bigger number. Well, negative 7, even though it's not very big, is still bigger than negative 10. And so in this particular case, even though we're working with a known strong acid, its concentration is so small that water is actually producing more hydrogen ions than our hydrochloric acid is. So we find the pH, this time from our hydrogen. pH equals a negative log of 1.0 times 10 to the negative 7th. We can use our little cheater rule. We don't have to pick up our calculator because our coefficient is 1. We're just going to take the opposite of our exponent. And so our pH is 7, which we know to be neutral. So here we have a strong acid present, but its concentration is so small that we actually have a neutral solution with a strong acid present. Okay, I think we are going to pause here, and I will post up this video for you, and then I will do a second video working with our weak acids and our weak bases.